Previously, we used Bayes' theorem to develop a systematic way of diagnostic decision-making. We did this by semi-quantitatively describing our belief about the presence or absence of a disease, both before and after the results of a diagnostic test were made available. We also saw that likelihood ratios were useful metrics to describe the effect of a test result on both the magnitude and direction of our belief. In this lecture, we will learn about two measures of diagnostic performance, sensitivity and specificity, and show the relationship to likelihood ratios. Our objectives are as follows. Introduce the performance metrics, sensitivity and specificity, and explain why they are ideal machine learning model performance metrics. And expand upon the concept of likelihood ratios, and show how they can be calculated from sensitivity and specificity. To make the argument that sensitivity and specificity are ideal diagnostic performance metrics, we first have to understand the features of ideal metrics. Say we've trained a model and we need to quantify how quote-unquote good the model is. We'll need some metrics that allow us to compare our model performance to previously well-established diagnostic tests, for example histopathology. That is, the metrics should allow for comparison between tests. Also, the metrics should allow us to compare the performance of that same model across different published studies or patient populations. Moreover, to be of practical use, these metrics should have an intuitive clinical meaning and guide our clinical decision-making. Now, because our model may be used at different hospitals or even different parts of the world, our performance metrics should hold despite differences in disease prevalence in patient populations. More succinctly, a metric should be invariant to disease prevalence. Finally, we'd hope our metric is actually measuring the ideas or concepts we care about, and we'd like for the measurement to be reliable. To illustrate this last point, a concrete though somewhat absurd example of a fairly reliable but non-valid metric would be the use of body temperature to measure a student's test performance. Though we could probably get consistent and repeatable temperature measurements, that is, reliable measurements, they would not be valid, since temperature is not a sensible measurement of a student's test performance. Sensitivity and specificity, the metrics we'll discuss today, have just these above ideal features. And because likelihood ratios are calculated from these metrics, they will necessarily have these features as well. A quick reminder of the Bayesian way of thinking. We have a prior belief about the probability that a disease is present. We then use the result of our diagnostic examinations to update both the direction and magnitude of our belief. And the result of this update is our posterior belief about the probability of disease presence. We'll now see where these likelihood ratios come from. Their calculations depend on the measured sensitivity and specificity of a diagnostic exam, so we'll first break down these terms. First, sensitivity. Sensitivity is a metric that quantifies the probability of a test being positive, given that a patient has the underlying disease or condition. It is expressed mathematically as follows, and is read: the sensitivity is equal to the probability of a positive test, given that the disease or condition is present. Now, how do we figure out the complement of this statement? That is, the probability of a negative test, given that the disease or condition is present. Remember that probabilities range from 0 to 1, indicating impossibility or certainty. For a given probabilistic experiment, with a given set of possible outcomes, the probability of any outcome of interest happening is 1. Take a fair coin toss. The probability of heads or tails is 1, since we are certain that the coin will land on either heads or tails. We will not take the coin landing on its side as a possible event. For the purposes of this discussion, our diagnostic test can only be positive or negative. Thus, the probability that the test is negative given the disease is present must be 1 minus the probability that the test is positive given the disease is present. That is, 1 minus sensitivity. Take a moment to confirm for yourself that this must be true. Now on to specificity. Specificity is a metric that quantifies the probability of a test being negative given that a patient does not have the underlying disease or condition. It is expressed mathematically as follows and is read: the specificity is equal to the probability of a negative test given that the disease or condition is absent. Again, let's figure out the complement of this statement, that is, the probability of a positive test given that the disease or condition is absent. Using the same reasoning as the prior example, the probability of a positive test, given that the disease or condition is absent, must be the complement of specificity, that is, 1 minus specificity. Again, take a moment to confirm for yourself that this must be true. Let's now build upon our prior knowledge of likelihood ratios. The likelihood ratio is a diagnostic performance metric used to determine whether a test result usefully changes the probability that a condition or disease is present. First, the positive likelihood ratio. The positive likelihood ratio is defined as follows. It is the ratio of the probability of the test being positive, given that the disease is present, over the probability of the test being positive, given that the disease is absent. Intuitively, if the numerator is much larger than the denominator, it means that a positive test result is much more likely to have occurred if the disease is in fact present. Note that a value of 1 indicates no effect on the posterior odds of disease. Think about what the value of 1 means. It states that the probability of the test being positive is the same whether or not the disease is present. Thus, we gain no new information to alter our prior belief. As the value of the positive likelihood ratio increases above 1, so do the posterior odds, or post-test probability, that the disease is present. To demonstrate, here is a table that relates the numerical value of the positive likelihood ratio to the approximate change in probability that the disease is present. Again, note that as the value of the positive likelihood ratio increases, so does our post-test probability of disease. Let's now repeat the thought process for the negative likelihood ratio. The negative likelihood ratio is defined as follows. It is the ratio of the probability of the test being negative, given that the disease is present, over the probability of the test being negative, given that the disease is absent. Intuitively, if the denominator is much larger than the numerator, it means that a negative test result is much more likely to have occurred if the disease is in fact absent. Again, see that a value of 1 indicates no effect on the posterior odds of disease. A value of 1 means that the probability of the test being negative is the same whether or not the disease is present. And again, we don't gain any new information to alter our prior belief. As the value of the negative likelihood ratio decreases below 1, so do the posterior odds that the disease is present. This table relates the numerical value of the negative likelihood ratio to the approximate change in probability that the disease is present. See that as the value of the negative likelihood ratio decreases, so does our post-test probability of disease. Okay, we've gotten a handle on positive and negative likelihood ratios. Our last step is to figure out how to calculate them by relating them to sensitivity and specificity. First, the positive likelihood ratio. Let's see if our knowledge and definitions of sensitivity and specificity will help us. We first noticed that the numerator term is the probability of a positive test result, given that the disease is present. Well, that's simply the sensitivity. How about the denominator? The denominator is the probability of a positive test result, given that the disease is absent. Well, this again sounds familiar. It's the complement of specificity. Let's now repeat the exercise for the negative likelihood ratio. The numerator term is the probability of a negative test result, given that the disease is present. That's the complement of sensitivity. The denominator term is the probability of a negative test result, given that the disease is absent. That's specificity. We see now an elegant way of relating sensitivity, specificity, and their complements to the likelihood ratios, and begin to understand why these would be ideal metrics to report the performance of our diagnostic models. Take a moment to notice that our now familiar Bayesian way of thinking can be expressed in the probability notation we've been using. Take a few moments to understand the meaning behind each term when expressed in such a way. First, for the situation in which the test result is positive, then for the situation in which the test result is negative. In summary, we've introduced the performance metrics, sensitivity, and specificity, and explained why they are ideal performance metrics. And we've expanded upon the concept of likelihood ratios, and learned how they can be calculated from sensitivity and specificity.